Every morning the sun rises and the world warms up. Plants grow, animals wake, oceans circulate. Everything alive on this planet runs on sunlight. We have built entire civilizations around that fact. We have worshipped the sun, studied it, painted it, and depended on it for every calorie we have ever consumed. And for most of human history, the assumption was simple: the sun keeps us alive. That assumption is not wrong, but it is dangerously incomplete. Because the sun is not a stable, constant source of warmth and light sitting politely in the sky. It is a violent, evolving, and increasingly dangerous star. And right now, at this moment, it is doing things to this planet that most people have never heard of. Not in a billion years. Not in a million years. Right now, today. The sun is slowly killing Earth, and we are only beginning to understand how many different ways it is doing it. Let's start with what the sun actually is, because most people picture it as a giant ball of fire, and that mental image is almost entirely wrong. The sun is not burning. Fire is a chemical reaction. It requires fuel and oxygen combining at the right temperatures and pressures to produce light and heat. The conditions inside the sun make ordinary combustion impossible. Temperatures at the core reach 15 million degrees Celsius, far beyond anything a chemical reaction could sustain. What is happening there is something fundamentally different and far more violent. Hydrogen atoms, moving at extraordinary speeds in that extreme heat, collide with enough force to overcome their natural repulsion and fuse together into helium. This process is called nuclear fusion, and every single second the sun converts approximately 600 million tons of hydrogen into helium. In that same second, about 4 million tons of mass are converted directly into pure energy according to Einstein's equation E equals mc squared. The energy released in 1 second of solar fusion is greater than all the electricity humanity has ever generated in its entire history combined. That energy takes roughly 100,000 years to travel from the core to the surface, bouncing between particles in a slow, chaotic, random walk. Then it leaves the surface as light and radiation and crosses 150 million kilometers of empty space to reach us in about 8 minutes. That is what sunrise actually is, the arrival of energy that started its journey before modern humans existed. The sun has been doing this for about 4.6 billion years. It has enough hydrogen fuel remaining to continue for roughly another 5 billion years. So it is, in the broadest sense, a middle-aged star. And here is the first problem. Middle-aged stars are not stable. They are getting brighter. Right now, the sun is approximately 30% brighter than it was when Earth formed. That number sounds enormous, and it is. Early Earth received significantly less solar energy than it does today. Scientists call this the faint young sun paradox, because geological evidence shows that early Earth had liquid oceans despite receiving far less sunlight than the amount that would keep water liquid today. The resolution involves higher concentrations of greenhouse gases in the early atmosphere, trapping what little heat there was. But the important takeaway is this: the sun's output has been climbing steadily for 4.6 billion years, and it will keep climbing. Over the next billion years, solar output will increase by another 10%. That does not sound like much, but for a planet with a finely tuned climate system, a 10% increase in incoming solar energy is catastrophic. Models show that within about 1 billion years, the additional heat will be enough to trigger a runaway evaporation of Earth's oceans. Water vapor will fill the atmosphere. Water vapor is itself a greenhouse gas, which will trap more heat, which will evaporate more water, which will trap more heat. The process feeds on itself until the oceans are gone and Earth's surface temperature climbs to levels that permanently end the possibility of complex life. Not the end of all life, perhaps. Some microbes might persist in extreme environments, but the planet we know, with its oceans and weather and forests and everything that has existed for hundreds of millions of years, ends. Not from an asteroid, not from a volcanic catastrophe. From the sun simply continuing to do what it has always done, just slightly more of it. But that is 1 billion years away, and the sun does not wait 1 billion years between attacks. In September 1859, the most powerful solar storm ever recorded struck Earth. It is known as the Carrington event, named after British astronomer Richard Carrington, who observed the solar flare that preceded it. The flare was so bright, Carrington initially thought his telescope was malfunctioning. Within 18 hours, a massive wave of charged particles called a coronal mass ejection reached Earth and slammed into its magnetic field. The aurora borealis, normally visible only near the poles, was seen as far south as Cuba and Hawaii. Telegraph systems across Europe and North America failed completely. Some telegraph operators reported receiving electric shocks from their equipment. Some lines continued transmitting messages even after operators disconnected the power, running purely on the electricity induced by the geomagnetic storm. The event lasted roughly 2 days. It was beautiful and terrifying in equal measure. And in 1859, the damage it caused was relatively limited because human civilization ran on almost no electricity. Now consider what would happen if the same event occurred today. Modern civilization runs on electricity, not just for convenience, for everything: water treatment plants, food supply chains, hospital equipment, banking systems, telecommunications, GPS navigation used by aircraft, ships and emergency services, the internet. All of it depends on electrical infrastructure that is profoundly vulnerable to geomagnetic storms of the Carrington magnitude. A study commissioned by the United States government estimated that a Carrington-level event today could cause between $1 and $2 trillion in damage in the first year alone. Transformers that take 12 to 18 months to manufacture and replace would be destroyed across entire continents simultaneously. Satellites in low Earth orbit would be knocked out or severely damaged. The GPS system, which aviation, shipping and military operations depend on globally, could be disrupted for weeks or months. In the most severe scenarios, large sections of the power grid in North America, Europe and parts of Asia could be down for months to years, not days. The cascading failures that would follow in food distribution, water supply, heating, medical care are difficult to fully model, but researchers who have studied them use the word catastrophic without hesitation. And here is the part nobody talks about. A Carrington-level event is not a once-in-a-millennium freak occurrence. It is a statistically regular feature of the sun's behavior. Research published in 2012 estimated the probability of a Carrington-level event hitting Earth in any given decade at roughly 12%. In 2012, a solar ejection of Carrington magnitude actually did occur. It narrowly missed Earth by a margin of about 9 days. If Earth had been in a slightly different position in its orbit, that storm would have hit us directly. We did not know about it until it was already past us. But the sun's threat to Earth is not only about what it hurls at us, it is also about what it is slowly taking away. Mars was not always the cold, dry, nearly airless desert it is today. 4 billion years ago, Mars had a thick atmosphere. It had liquid water flowing across its surface. There is geological evidence of ancient rivers, lake beds, and possibly even shallow seas. The conditions for life, as best we understand them, existed on Mars for hundreds of millions of years. And then something stripped that atmosphere away. That something was the solar wind. The solar wind is not wind in any familiar sense. It is a continuous stream of charged particles, mostly electrons and protons, flowing outward from the sun in all directions at speeds of roughly 400 to 800 kilometers per second. It never stops. Every planet in the solar system is constantly bathed in this stream of particles. What protects Earth from it is our magnetic field. Generated by the motion of molten iron in Earth's outer core, our magnetic field deflects the solar wind around the planet, creating a protective bubble called the magnetosphere. Without it, The solar wind would do to Earth's atmosphere exactly what it did to Mars. It would gradually strip away the lighter molecules at the top of the atmosphere, eroding it over millions of years until it became too thin to support liquid water or complex life. Mars lost its magnetic field roughly 4 billion years ago when its smaller core cooled and solidified, shutting down the dynamo that generated the field. Within a few 100 million years after that, the solar wind had stripped away most of its atmosphere. The water evaporated or froze. The surface became the barren, irradiated landscape we see today. Earth's magnetic field is what separates us from that fate. And here is the problem. Earth's magnetic field is weakening. Over the past 200 years, since humans began measuring it systematically, Earth's magnetic field has weakened by approximately 9%. That is not a smooth linear decline. The field fluctuates. It has been stronger in the past and weaker in the past. It reverses polarity periodically, a process called geomagnetic reversal, in which the north and south magnetic poles swap positions. These reversals have happened hundreds of times in Earth's history. The geological record shows they occur roughly every 200,000 to 300,000 years on average. The last full reversal was approximately 780,000 years ago. We are, statistically speaking, overdue. During a reversal, the magnetic field does not simply flip overnight. It weakens, becomes chaotic and fragmented, with multiple poles appearing at lower latitudes, and then rebuilds in the opposite orientation. This process can take anywhere from a few hundred to a few thousand years. During that time, Earth's protection against the solar wind is significantly reduced. Radiation levels at the surface increase. The aurora would be visible at the equator. Satellites and GPS systems would face severe disruption. Whether past reversals caused mass extinctions is still debated, but the exposure to increased radiation during the weakened period is not hypothetical, it is physics. And the weakening is not only in the total strength of the field. There is a specific region over the South Atlantic, roughly between South America and Africa, where the magnetic field is already dramatically weaker than everywhere else. Scientists call it the South Atlantic anomaly. Satellites passing over this region regularly experience higher rates of software errors and hardware malfunctions caused by the increased particle radiation penetrating the weakened field. The International Space Station increases radiation monitoring for crew members when its orbit takes it through this region. The anomaly is growing. In recent decades it has expanded and its center has shifted westward. Some researchers believe it may be a precursor to a geomagnetic reversal or to the field splitting into separate poles. Nobody knows for certain. What is certain is that the sun's particles are finding it easier to get through in that region, and the region is getting bigger. There is one more thing the sun does that most people have never heard of, and it is happening right now with more intensity than at any point in the last decade. The sun operates on an 11-year activity cycle. During solar minimum, sunspot activity is low and the sun is relatively quiet. During solar maximum, sunspot activity peaks. Solar flares become more frequent and more powerful, and coronal mass ejections become more common and more energetic. We are currently in solar cycle 25. Scientists initially predicted it would be a below-average cycle, relatively quiet and unremarkable. They were wrong. Solar cycle 25 has been significantly more active than predicted, with sunspot counts and flare activity consistently exceeding expectations. In 2024, the sun produced the strongest solar flare in nearly 2 decades. In May 2024, a series of powerful geomagnetic storms struck Earth, the strongest since 2003, producing auroras visible across large parts of the United States and Europe at latitudes where they are almost never seen. Power grid operators across North America issued warnings. Some satellite operators reported anomalies. The storms were disruptive but not catastrophic. They were also a reminder of what the sun is capable of, and a demonstration that we are not in a period of solar quiet. We are in a period of solar maximum, and the Sun is more active right now than it has been in years. NASA's Parker solar probe has been flying closer to the Sun than any spacecraft in history, diving inside the corona, the Sun's outer atmosphere, and sending back data that is fundamentally changing our understanding of how the Sun works. One of the most significant discoveries has been about why the corona is so much hotter than the surface. The Sun's visible surface is approximately 5,500 degrees Celsius. The corona above it reaches temperatures of 1 to 3 million degrees Celsius. For decades, this made no physical sense. Heat normally flows from hot to cool, not from a cooler surface into a hotter atmosphere above it. Parker has found evidence that the corona is heated by tiny, rapid magnetic reconnection events called nanoflares, happening constantly across the Sun's surface and injecting enormous amounts of energy into the corona. This matters because understanding what heats the corona is directly connected to understanding what drives solar wind and what triggers the most powerful and dangerous solar eruptions. The better we understand the mechanism, the better we can predict when the next major coronal mass ejection is coming and how powerful it will be. Right now, our best warning time for a major solar storm is roughly 15 to 45 minutes from the moment it is detected. That is not enough time to protect critical infrastructure. Improving that warning time is one of the most important unsolved problems in space weather science. So we have the Sun getting brighter over geological time, threatening to boil away the oceans within 1 billion years. We have Carrington-level events occurring regularly on astronomical timescales, with a non-trivial chance of hitting us in any given decade. We have the solar wind slowly working on our atmosphere in the background, held back only by a magnetic field that is weakening and possibly preparing to reverse. But we have not even discussed what the Sun is going to do at the end of its life, and the end of its life does not arrive suddenly. The Sun begins changing everything in the solar system long before it physically expands. In approximately 5 billion years, the Sun will exhaust the hydrogen in its core. At that point, the core will begin to contract under gravity while the outer layers expand outward. The Sun will become what astronomers call a red giant. During this expansion phase, it will grow to roughly 200 times its current diameter. Whether it will physically engulf Earth is actually uncertain. Some models suggest Earth will be swallowed. Others suggest Earth will spiral outward as the Sun loses mass, staying just ahead of the expanding surface. Either way, the outcome for Earth is identical. Long before the Sun physically reaches it, the increased luminosity of the expanding Sun will have raised Earth's surface temperature to levels that vaporize rock. The oceans will be gone, the atmosphere will be stripped away. The surface will be a molten, barren landscape orbiting inside the outer atmosphere of a dying star. Everything that has ever lived on this planet, every species, every ecosystem, every trace of every civilization will be erased completely. And here is the thing that is genuinely hard to sit with. None of this is a disaster in any human sense of the word. No asteroid, no sudden catastrophe, no enemy. The Sun is not doing anything wrong. It is simply evolving according to the laws of physics, the same way it has for 4.6 billion years. It made us possible. The carbon in your body, the oxygen you are breathing, were forged inside earlier generations of stars that lived and died before our Sun formed. The iron in your blood was produced in the cores of massive stars far larger than our Sun, and scattered across space when those stars exploded as supernovae. The debris from those deaths seeded the cloud of gas and dust that eventually collapsed to form our solar system. We are, in a very literal sense, made of star material. And the star that made us possible is also the one that will, eventually and inevitably, take everything back. But here is what that actually means for the present. Not the billion-year future. Not the 5 billion-year future. Now, we live on a planet that is protected from a violent star by a magnetic field we did not build and cannot control. that is currently weakening for reasons we do not fully understand. We have electrical infrastructure worth tens of trillions of dollars that would be severely damaged by a solar storm that has roughly a 12% chance of occurring in any given decade. We have a star that has increased its output by 30% since Earth formed and will continue increasing it until the oceans are gone. And we spend almost no time thinking about any of this because the sun rises every morning looking exactly the same as it always has, warm and steady and familiar, and nothing about its appearance tells you what it is actually doing. There is no visible sign on a calm morning that the same object producing that warm light is also bombarding us with X-rays, ultraviolet radiation, and energetic particles that our atmosphere and magnetic field are quietly absorbing and deflecting around the clock. The ultraviolet radiation alone, the fraction that does make it through the atmosphere, is the leading cause of skin cancer globally. It damages DNA, it suppresses immune function, it degrades plastics, synthetic materials, and exposed organic matter. The atmosphere absorbs roughly 97 to 99% of the sun's ultraviolet output before it reaches the surface. That protection depends on the ozone layer, a thin band of ozone molecules in the stratosphere that absorbs UV radiation and converts it to heat. The ozone layer is not self-maintaining in any unconditional sense. It is a chemical equilibrium that can be disrupted. We disrupted it with chlorofluorocarbon compounds in the 20th century, opening the ozone hole over Antarctica. We have partially repaired it through international agreements, but the point is that the sun's ultraviolet output, which we take for granted as something the atmosphere handles, is only handled because of a thin layer of gas chemistry that turned out to be more fragile than anyone realized until we accidentally started breaking it. That is perhaps the most unsettling thing about the sun. It does not look dangerous. It looks like light. It looks like warmth. It looks like the reason anything is alive at all, and all of those things are true. The sun is the reason we exist. It is also the reason we will not exist forever. And the distance between those two facts is shorter than most people realize. The next time you watch a sunrise, you are watching a nuclear furnace 150 million kilometers away that has been getting slightly more dangerous every single year for 4.6 billion years. A furnace that hurls billion-ton clouds of magnetized plasma at us regularly. That is slowly stripping away the atmospheres of planets without magnetic protection, exactly as it did to Mars. That will eventually grow large enough to swallow everything we have ever known. And that is currently more active than it has been in years, producing the strongest storms in 2 decades, while our infrastructure sits exposed and our warning systems give us less than an hour's notice. It is beautiful, and it is not peaceful. It never was. If you enjoyed this video, consider subscribing. I will see you in the next one.